Вітаю, шановні
Greetings, dear
спільноти.
community. I have been working on the problem of separating individual musical instruments from a combined audio stream for quite some time. It all began when I was very proud of a remastering I had done of a recording by Jascha Heifetz. However, a violinist friend of mine quickly brought me back down to earth and told me that I had simply killed Heifetz's violin. It was hard to hear, but the truth is difficult to argue with. If you enhance Heifetz's violin, the orchestra begins to fall apart. If you restore the orchestra, the violin loses its voice. Until you can separate one from the other, it is impossible to achieve a truly accurate result. You can make it sound beautiful, but that does not necessarily make it true. I studied Alan Downey's DSP textbook, for which I am deeply grateful to him, but eventually I came to the conclusion that it was not enough. A different approach was needed, one based on music itself. For me, music has always been the expression of abstract mathematical structures. It is inherently logical, governed by strict rules, and capable of revealing relationships that can be described numerically. At least that is how I see it. For that reason, I set out to translate musical logic into an algorithm that a computer could understand. Today, I am pleased to present the result. So, under the flag of Antonio Salieri, let us explore what I call the mathematics of resonance. From music theory to the internal structure of a note. Almost everyone who has received a musical education has seen a diagram like this. It represents the overtone series, a sequence of tones naturally produced by a vibrating string, the human voice, or any musical instrument. This series forms the foundation of musical intervals, chords, scales, and ultimately the entire tempered musical system. Traditionally, this diagram is studied as part of music theory, but what happens if we look inside a real musical sound? To explore this question, let us take a single violin note and examine its spectrum. On the screen, we can see a series of peaks distributed across different frequencies. At first glance, these peaks may appear random. However, if we look more carefully, a remarkable pattern begins to emerge. The overtone diagram familiar from music theory does not merely describe a theoretical concept. It also describes the internal structure of a real musical sound. Each peak corresponds to a harmonic generated by the vibration of the string. The lowest frequency is called the fundamental tone. Above it appear harmonics whose frequencies are integer multiples of the fundamental frequency. If we denote the fundamental frequency as F1, then the following harmonics occur at F2 equals 2 times F1, F3 equals 3 times F1, F4 equals 4 times F1, and so on. Now let us look at the same note once again. Pay attention to the spacing between neighboring peaks. Despite the complexity of a real instrument, the peaks align into a sequence that reflects the harmonic multiples of the fundamental frequency. This is why the overtone series is much more than a theoretical diagram. It represents the actual physical structure of musical sound. This observation serves as the starting point of our study. Now that we have seen how a musical note is organized internally, we can move on to the next question. How does the tempered musical system emerge from this harmonic structure? Foundations of duodecimal musical notation. We can now examine the notation system used throughout this study. The foundation of the modern musical system is the tempered scale. Each successive semitone is obtained by multiplying the frequency by the 12th root of 2. After 12 such steps, the frequency doubles, producing the next octave. As a result, any musical note can be described by two parameters: its position within an octave and its octave number. To represent the position of a note within an octave, a duodecimal numbering system is used. In this system, each pitch class is assigned a unique symbol. The note C is represented by the digit 1. C sharp or D flat is represented by 2. D is represented by 3. The sequence continues through the complete cycle of 12 pitch classes. The final 3 values are represented by the symbols A, B, and C. Thus, the entire 12-step cycle is written as 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. The next element of the system is octave assignment. 2 reference points are used. The region around 1 Hz corresponds to octave 1. The standard tuning reference of 440 Hz corresponds to the note 9A. Each successive octave doubles the frequency. For this reason, octave labels also follow duodecimal numbering. After 9 come A, B, and C, followed by 11, 12, and so on. By combining the octave number with the pitch class identifier, we obtain a complete note designation. For example, 9.1, 9.5, 9.A, 9.CA period is used to separate the octave number from the pitch class identifier. Following the note designation, a special structural symbol is used, the apostrophe. This symbol is not related to note duration. It is used solely to provide a structured representation of note data. When the apostrophe is followed by a hyphen, no microshift is present, indicating the ideal theoretical position of the note. Thus, the notation, 9A', represents the note A in octave 9, with no microshift relative to its theoretical position. As we will see later, real musical sounds rarely coincide perfectly with their ideal coordinates. To describe these deviations, the system introduces microshifts. However, the organization of microshifts will be discussed later, after the construction of the resonance spiral. 12-tone resonance spiral coordinate system. We have now established a notation system capable of describing musical notes within the tempered scale. The next question is whether these relationships can be represented geometrically. At first glance, musical notes can be represented using a keyboard layout or a linear frequency scale. However, these representations hide an important property of musical space. Notes belonging to the same pitch class family preserve their musical identity regardless of octave. For example, the note A remains the note A whether it sounds at 55 Hz, 220 Hz, 440 Hz, or 1760 Hz. We therefore require a geometry capable of representing both frequency growth and pitch class identity at the same time. For this purpose, a resonance spiral is constructed. Within this system, every note receives its own coordinate. The angular position identifies the pitch class family. The radial position represents octave growth. As we move away from the center, frequency increases according to the same law that defines the tempered musical system, the 12th root of 2. Each new point therefore corresponds to the next step of the tempered scale. At this point, an important distinction must be made. In this work, the geometry is not imposed in advance. Instead, it is derived directly from the resonance relationships of the tempered scale. The angular sectors are calculated using the same resonance constant that governs frequency growth. As a result, the sectors are not equal. Their dimensions are determined by resonance relationships rather than geometric symmetry. Although the sector angles differ, their sum still completes a full 360-degree cycle. Let us now see how this coordinate system is interpreted. Notes belonging to the same pitch class family align along a common radial direction. For example, all A notes form a single radial family. The same principle applies to every other pitch class. After completing a full 12-step cycle, the system returns to the same pitch class family while occupying a new radial level. In this way, octave repetition becomes visible as a geometric pattern. The resonance spiral transforms musical relationships into spatial relationships. It becomes a coordinate framework within which real musical sounds and their harmonic structures can be analyzed. Having established the resonance spiral, we can now proceed to the next stage of the study, the organization of microshifts and their role in the structure of resonance space. From the overtone series to microshifts. Let us return to the overtone series diagram familiar to every musician. Even here we can observe an important detail. Not all harmonics fall exactly on the coordinates of the tempered scale. For this reason, music theory uses special markings to indicate deviations from ideal tempered positions. Some harmonics appear slightly higher than expected. Others appear slightly lower. The reason is that real sound almost never exists under ideal conditions. Every instrument possesses its own resonant structure. Every string, soundboard, air column, and resonant body influences the distribution of energy. As a result, real resonant states rarely coincide perfectly with their theoretical coordinates. To describe these deviations, the system introduces microshifts. Their purpose is not to create new notes. Their purpose is to describe the position of a real resonant state relative to an ideal coordinate. Let us examine the space between two neighboring notes of the tempered scale. In this example, the segment between 9.9 and 9.A. This space is organized according to the same resonance principle used to construct the entire spiral. For this reason, microshifts are not based on a simple linear subdivision of a semitone. They inherit the same resonance geometry. Each semitone can be refined using a system of microshifts. The identity of the note remains unchanged. Only the position of the resonance center within the local region is modified. Two prefixes are used to indicate the direction of displacement. The symbol I denotes a tendency toward the next pitch class. The symbol A denotes a tendency toward the previous pitch class. It is important to emphasize that these symbols are not equivalents of sharps or flats. They do not change the musical identity of the note. For example, the notation 9.9 apostrophe I. 3 represents the note 9.9 with a displacement of 3 microsteps toward the next coordinate. Similarly, 9.A prime A, 4 represents the note 9.A with a displacement of 4 microsteps toward the previous coordinate. In both cases, the note remains the same pitch class. Thus, microshifts do not create additional notes between existing notes. They describe real deviations of resonant states relative to the ideal coordinates of the tempered system. Microshifts therefore provide a way to preserve note identity while simultaneously describing the actual position of a resonant state within musical space. Time 60. The study of music also requires a principle of proportionality. In music, not only pitch is tempered, but time as well. A tempered pitch system requires a tempered time system. Therefore, the temporal axis must have its own method of subdivision. Musical time possesses a complex internal structure that includes meters, note durations, pickup measures, dotted notes, and ties. If musical notes are organized into a coherent system, then time should be organized according to the same principle. To describe these phenomena, we introduce the time 60 system, in which 1 second is divided into 60 parts and can be further refined into progressively smaller temporal levels. This approach provides a unified coordinate framework for representing pitch, rhythm, and the evolution of resonant structures in time. Now let us look at how the harmonics of the note A in the second octave, designated in our notation as 9A, are arranged on the spiral. In this representation, the theoretical harmonic series is shown not only as a set of frequencies, but also as a spatial structure. And now let us add the time axis and see what this note looks like in reality. In front of you is a projection of the note A, played on the fourth string of a violin and scanned by the algorithm. We can see that all harmonics appear in their expected positions, while many of them have their own microshifts. For a real musical sound, this is completely normal. We can follow the life of the harmonics over time. We can observe the vibration of the string itself. The fundamental tone and the harmonics most closely related to it remain relatively stable, while the 5th, 7th, 10th, and 11th harmonics visibly oscillate, effectively revealing the motion of the string. Interestingly, these very harmonics help distinguish the same note played in different octaves, but that is not all. The algorithm also identifies resonant relationships, and the next layer represents the resonant response of the instrument body. It is easy to see that this is neither noise nor chaos. It is a real resonant response that exists throughout the entire duration of the note. But there is still another layer. The next layer represents the secondary resonant response of the instrument body. What is especially interesting is that these responses are mostly concentrated in the lower range at the beginning, but toward the end of the note they spread into the higher frequencies. As a result, the raw data obtained from a WAV file contains surprisingly little actual noise. When analyzed through musical and resonant relationships, it becomes a set of characteristics that can be used to identify instruments. This is how only the harmonic structure of the instrument sounds. Without the body response and without the secondary resonances, this is how only the instrument body sounds. And this is how only the secondary resonances sound. And this is how all of them sound together. The note recognition pipeline is available on GitHub. If you wish, you can examine the method yourself and generate your own scans of individual notes. Now let us look at comparative projections of the same note played by different instruments. Right now, you are looking at a comparison between a cello and a violin. These instruments are very close in character. To an untrained listener, they may sometimes sound similar, although a musician can easily tell them apart. Let us temporarily disable the instrument body responses and the secondary resonances. As expected, the harmonic structures are based on the same musical principles. The harmonics occupy similar positions. However, their behavior is different. The lower harmonics remain relatively stable, but as we move higher in the harmonic chain, visible oscillations begin to appear. These oscillations reflect the vibration of the string itself. The blue projection represents the cello. The cello strings are longer, and because of that, their oscillations are more pronounced. This allows us to observe one of the differences between a violin and a cello. Now let us add the resonant response of the instrument body. The cello is shown in blue and the violin in orange. The body response of the cello is much richer and occupies a significantly larger volume. This is exactly what we would expect from a larger instrument. Now let us look at the secondary resonant responses. Here the difference becomes even more obvious. The secondary responses of the two instruments are almost completely different. The body response and the secondary resonances provide additional characteristics that help distinguish one instrument from another. Now let us compare a banjo and a guitar. These instruments sound very different, but they produce sound in a similar way. Both rely on vibrating strings. Even when we look only at the harmonic structures, we can immediately see that the strings behave differently. The life of the harmonics is completely different for the two instruments. Only the lowest harmonics remain relatively similar. As the note develops, the higher harmonics of the banjo begin to break apart and lose stability. The guitar behaves differently, maintaining a more continuous harmonic structure. Now let us add the resonant response of the instrument body. Here we can see that the two instruments have almost nothing in common. Their body responses occupy very different regions of the resonant space. and the difference becomes even more obvious when we look at the secondary resonances. Together, the body response and the secondary resonances reveal just how energetic and complex the banjo can be. In a sense, they show why the banjo has such a bright and distinctive character. The guitar, on the other hand, produces more restrained and controlled resonant responses. These additional resonant layers become powerful characteristics for distinguishing one instrument from another. Now let us compare two very different instruments, an acoustic bass guitar and a piano. Both instruments produce a rich and full sound, but their harmonic structures are not identical. Some harmonics occupy similar positions, while others differ noticeably. One of the reasons is the tension of the strings. In a piano, the strings are stretched much more tightly. As a result, the harmonics form remarkably stable vertical structures. In the acoustic bass guitar, we can clearly observe the vibration of the string itself. The harmonics are less rigid and show visible oscillations over time. Now let us add the resonant response of the instrument body. The piano body is much larger and generates a much stronger resonant response. This is immediately visible in the projection. Finally, let us look at the secondary resonances. The blue projection represents the acoustic bass guitar. The purple projection represents the piano. These secondary resonances are completely different. Even when two instruments produce notes of similar pitch, their resonant behavior remains unique. The body response and the secondary resonances provide additional information that helps characterize and distinguish different instruments. The article Duodecimal Resonant Numeration, Resonance Structure. Datasets and spiral space visualizations has been published on Zenodo. Part of the Duodecimal Resonant Numeration project is also available on GitHub. If you decide to explore the project yourself, there is one thing worth mentioning. At the current stage, the calculations require a considerable amount of time by modern standards. The reason is simple. The algorithm is designed to collect as much information as possible from a WAV file rather than perform a quick scan and discard most of the data. Individual instrument notes represent laboratory conditions. Everything is clean, isolated, and easy to observe. Real music is very different. In an actual musical performance, all sounds interact, overlap, and influence one another. Because of this, the current stage of the research focuses on finding resonant relationships. Let us take a small fragment of Ave Maria as an example. Here the algorithm is no longer searching for a note. It is no longer searching for a specific instrument. Instead, it searches for a cloud of resonant relationships. You may think of it as an attractor with its own life, unfolding through time. The resonant cloud is shown in green. Everything else is shown in red. Some parts of this cloud intersect with harmonics produced by other instruments. However, the algorithm is currently focused on resonant relationships themselves. It analyzes how one resonant event gives rise to another, following a parent-child principle through time. At this stage, long musical events provide the best environment for developing and refining the method. And at the moment, this resonant cloud sounds like this. Of course, this is only a small step. It is not yet a complete extraction of an instrument from a musical recording. But it is worth remembering that digital photography once began with only 4 pixels. Compared to where that technology eventually arrived, the future possibilities of this approach seem quite promising.
Дякую, що приділили увагу цьому
Thank you for your
матеріалу.
attention.
Якщо
If you have
у
any
когось
questions or
виникнуть
suggestions, the
запитання
conference
або
organizers will be
пропозиції,
happy to
мої
provide my
контакти
contact
є у
information.
організаторів конференції. До побачення. Слава Україні!